So some of you guys may be familiar with this idea of distance is equal to the rate times the time. And how do I say this? The canonical real life situation that we're applying a lot of this calculus stuff to is kind of motion of an object as it moves in a straight line. So you guys are probably aware that we work with position, then velocity, then acceleration, right? And of those three things, position, velocity, and acceleration, the one that's a rate of change is velocity. So what I can do is I can create a little set of axes over here. And I can put the time on the horizontal axis and the velocity on the vertical axis. And if I had just a horizontal line like this, that means I have a constant velocity. Okay. So let's say that my picture looked like this. Let's say this was 60 miles per hour and you were driving for 3 hours. Then how far did you go? Well, you had 60 miles per hour. Then you drive for 3 hours. What you notice is that the units for hours on the denominator and hours on the numerator cancel out, and you end up with 180 miles. So all this is saying is if you drove at a constant speed, then you just multiply the velocity times the time that you drove, and that's going to give you the total distance that you traveled. I hope this is common sense. This situation, though, is specific to the fact that the rate was constant. The rate's not always constant, right? You could be going faster sometimes and slower other times, and that rate could be changing in a continuous way. So if you looked at this, oh my God, it literally drew the same picture right here. I think I do this all the time. And I literally did the same. Yes. Anyways, my point was that if you look at this picture, we have a velocity that's changing. So all we do is we do the same thing that we did at the beginning of class. It's just contextualized in this distance, rate, and time scenario. So your velocity is going to be on the y-axis. Your time is on the x-axis. And we can approximate the area under this curve, which the distance we traveled, with the areas of rectangles. So in our case, we had this 24 meters situation. Now, if you made these rectangles, if you had more rectangles, then your approximation would be better. If you let the number of rectangles go to infinity, then that would give you the true distance that you've traveled. So this last section is really just what we had been doing before, just wrapped in this framework involving time, velocity to calculate the distance. Okay. All right, great. So let's move on to 4.2.